Okay, so this is Geometry 12-2, chords and arcs. Our objective today, students will be able to use chords, arcs, and central angles, perpendicular bisectors as chords. Okay, so those are it. Students will be able to use chords, arcs, and central angles and perpendicular bisectors of chords. Now, we've got that objective here at the top of our notes. The definition of a chord is a segment whose endpoints are on a circle. In central understanding today, you can use information about congruent parts of a circle to find information about other parts of a circle. But let's investigate this chord. This chord PQ, the endpoints are on the circle, and this can be moved all over the circle. And we can have multiple chords on a circle. And as you go through, you worked with chords before. The most popular chord you worked with is the diameter. If I can actually get this straight across, let's pretend that this is a straight red line. Okay, my diameter is a chord that goes through the center. Now, going on in our notes, theorem 12-4 and its converse. The theorem originally is, within a circle or in congruent circles, congruent central angles have congruent arcs. So if I have angle AOB congruent to angle DOC, then the arc they intercept, this arc they intercept, this arc that they intercept are therefore congruent. You got to remember that these arcs are an angle measure. They're the same measure as the angle, the central angle that intercepts them. The central angle is the angle whose vertex is on the center of the circle. So within a circle or in congruent circles, congruent central angles have congruent arcs. So we've got that going on. Now its converse, and let me take care of the markings I put in there. The converse, within a circle or in congruent circles, congruent arcs have congruent central angles. So the first one was if the angles are the same, then the arcs are the same. The second one, if the arcs are the same, then the angles are the same. So when we do a converse, we switch the first part of the sentence and the second part of the sentence. We learned that earlier in the year as hypothesis and conclusion. So the hypothesis goes to the conclusion and the conclusion goes to the hypothesis when we do a converse. Now in 12-5 and its converse, we're looking at within a circle or in congruent circles, congruent central angles have congruent chords. So if I'm looking at congruent central angles and congruent chords, this picture looks a lot like the other one we have, except for the fact that we have chords coming from the endpoints of our angles that come in contact with our circle. So these two blue chords are the same size. They're defined by our congruent angles, and they come in contact here at B and A and C and D. So if my angles are congruent and they define congruent arcs, then my chords that connect the endpoints of the congruent arcs or even the angles are going to be congruent as well. Now, the converse of this, within a circle or in congruent circles, congruent chords have congruent central angles. That converse is true. So I have central angle, and then it creates congruent chords. Well, I have congruent chords, and then I can have central angles that are defined by those chords from the endpoints of the angle going to the center and back out to the other endpoint of the chord. In our problem here in 12-6, or a theorem in 12-6 and its converse, within a circle or in congruent circles, congruent chords have congruent arcs. Now I alluded to that in the previous example, but if I have a congruent chord here, this chord and this chord define the same arc. These arcs are congruent, defined by these chords. The chords are the straight lines, okay? The chords are the straight lines, okay? They're congruent. Therefore, the arc that they define, the intercept at the endpoints, are congruent as well. Now, just to touch on the converse here, within a circle or in congruent circles, congruent arcs have congruent chords. Well, if I got congruent arcs, I have congruent chords. So the converse here is true. So this is a list pretty much of theorems and their converses, 12-4, 12-5, and 12-6. Now, how do we use this? For each pair of circles, circle X is congruent to circle E. What you can conclude. Now, I'm going to use 12.4, 12.5, and 12.6, those things that we just looked through. I have PQ with it's a chord congruent to SR. And now I've got some folks going, how do you know it's congruent? Well, I've got this vertical angle going through here. This is a vertical angle here and here. And I want to make sure that you see this vertical angle coming through here. Now they're telling me that PQ and AB are congruent, but it's not just that I have arc PQ and arc AB congruent. Let's just look at our angles first here. I've got vertical angles, and I've got chord PQ and chord SR congruent to each other, along with chord AB and chord DC congruent to each other. I have arc PQ and arc SR and arc AB and arc DC. Not only are they congruent inside each circle, but they're congruent across circles because of these statements that these two chords are congruent. So I know chord PQ is congruent to chord SR, which is congruent to chord AB, congruent to chord DC. They're all congruent. I also know that these angles, because they're vertical angles, PXQ and RXS are congruent, but they're also congruent to AEB and DEC. And then lastly, we talked about the arcs, and the arcs PQ and the arc SR and the arc AB and the arc DC are all congruent to each other because of this one marking at the beginning of this, and that the circles are congruent themselves. So that's what I can conclude with just this one marking here, and I'm just focusing on the marking itself and the angles and chords and arcs that are connected to that one mark. There are other things that are congruent in those circles, but I'm focusing in on that just one mark. Now, I would like you to look at the mark provided here in these two circles and see what you can conclude. Now, hopefully you're seeing that when I'm looking at this, because the arcs are congruent, arc DF and arc WY are congruent to each other, I have angle YXW and angle DEF congruent to each other. So I wrote it WXY, and I have angle DEF congruent to each other. I also have chord WY and chord DF congruent to each other. So I have WY or YW congruent to chord FD. Okay, so keep those in mind. Just from this one marking, I'm able to say that about these two things. Now, in theorem 12.7, in its converse, within a circle or congruent circles, chords equidistant from the center or centers are congruent. So if I have this chord, and they're the same distance, and it's a perpendicular distance from the center, if they're perpendicular distance from the center, okay, and they're the same, then I know these two chords are the same. Okay, and the converse of that is true. If I know two chords are congruent, then I know that their perpendicular distance from the center of the circle are identical. Okay, so how can I use this? When I'm looking at a problem here, I know that this is 9 and this is 9. So consequently, SR and PR are congruent chords. They're the same length. If this is 12.5 and this is 12.5, this therefore must be 12.5 plus 12.5, which is 25. And this is what I'm doing. I'm saying that SR, and PR are the same. SR is equal to PQ plus QR. So I know that SR must be 25. Okay, and that was the reasoning I put together, and you did too. I just wanted to write it down using our geometry skills. Remember, SR means the distance between point S and point R. PR, the distance between point P and point R. So keep those in mind. This type of notation is going to come back, and we're just going to say, hey, find PQ. And I say, hey, PQ's right here, and that distance is 12.5. Okay, as an example. Now, it's your turn. I want you to turn me off and try this one. Okay, so you got it. What is the value of X? Justify your answer. 18 and 18, right? This is 16. 18 plus 18 is 36. This is 36. These are perpendicular. This must therefore be 16. Congruent chords are equidistant from the center. These two chords are congruent. They've got to be the same distance from the center. So I know that x must be 16. Now, in theorem 12.8, in a circle, if a diameter is perpendicular to a chord, then it bisects the chord in its arc. Now, it's a lot like the last one we did, because that perpendicular each time will always split that chord in half. So if a diameter is perpendicular to the chord, then it bisects the chord in its arc. So this diameter is perpendicular to this chord, then it bisects the chord. So CE is equal to ED, and also it bisects the arc. So arc CA is also congruent to arc AD. So that's what we've got going on. So if I have perpendicular, I split the chord and I split the arc into two equal parts. Now, keep in mind, we've got the same thing going on in circle D. Segment ZX is the diameter of the circle and segment ZX perpendicular to segment WY. So ZX is perpendicular to WY. So this is an application of the last theorem we looked at. So since ZX is perpendicular to WY, I know that we're going to call this, I'm going to call this V. We're going to call this V. I forgot to leave my V in because I want to be able to talk about that. This point is V. So WV is congruent to segment VY. Okay, and WX is congruent to XY or YX. And I know this because ZX is the perpendicular bisector of not only the chord, but the arc itself. And that's got to be because it goes through the center. It's got to be the diameter. Now let's use some of these properties in problems. And you'll notice that most of these problems we use these properties in will, I don't know, maybe use Pythagorean theorem. So we have the Pythagorean theorem to pull out because why? We've got this situation. I've got K going down here, KL, and N. This is a right triangle. I know this height is 3. I know this length is 14, but because of the properties we just learned, I have a diameter that's perpendicular to the chord, and I got some people that are saying, Bloom, that's not a diameter, that's just a segment. But it can be contained in a diameter. And if that's true, I'm splitting this chord into two equal parts. So this is 7, and so is this side. Okay, so I've got this is 7, 7, that makes my 14. So I have a right triangle that has two legs of 3 and 7. Hey, I've got a right triangle. Let's use Pythagorean theorem. And I got a leg of 7 and 3. I have 49 plus 9, which is 58. So I'm going to take the square root of 58r. So I put that in my calculator, and I'm going to take, I can do that square root in two different ways. I can raise it to the 1/2 power, like this, or I can hit my math key, and I lied, it's square root. Let's go back. Let's go as quit. Okay, I can hit my square root key and put 58 inside, and do it that way. Either way, I get 7.6. They want me to round to the nearest tenth. The nearest tenth is the first digit past the decimal, so it's 7.6. And that's my value for R. So R is 7.6 centimeters, and perhaps I should write in there that R is 7.6 centimeters, so you all know. So R is equal to 7.6 centimeters. Now in our next problem, we have something very similar, except instead of looking for the radius, we're kind of given enough information to find the radius here. Okay, So I have a diameter and I'm sneakily hiding it in another part of the shape. So it's hard to see that that diameter can be broken down as 2 radiuses of 9. 18 divided by 2. So now, now I've got this right triangle with a hypotenuse of 9, a leg of x, and I'm thinking that this is going to be 7 again, because it's a chord that's split by something that could be the diameter coming through there. So this is also 7. So I have a right triangle here. And again, because I have a right triangle, I bring out Pythagorean theorem. Except in this case, I have my 9 as c. And so I've got 7 squared plus x squared is equal to 9 squared. So I got 49 plus x squared is equal to 81. I subtract 49 from 81 and get 32. I'm going to take the square root of 32 and find out that it's 4 the square root of 2, or if I put it in my calculator, I'll put in my second, and I'll hit 32, and I got 5.7 rounded to the nearest tenth. Now, keep in mind, I don't have any units here, so I just know that x is equal to that, so that's my value of x they wanted me to find. Now, I want you to make sure that you start recognizing some things. In problems like B, this is a real popular question to have on ACT, SAT, MCA type questions, because they'll give you the radius of a circle and they'll give you a sketch like what we've been doing, okay? Now, notice that these are both 11, okay? I need you to notice that those are both 11 coming through here. This is y coming up, and then I have my 15 for my radius. If I close my radius in, like it is here on this dotted line, it's really easy to see the triangle that could be made. I want you to recognize that because they're both 11 and y is coming from the center, that this should be a right triangle. And so as I close this, the radius stays consistent, and you need to recognize that that is still 15. I have a right triangle with a leg of 11, a leg of y, and a radius slash hypotenuse of 15. So I can take my Pythagorean theorem, and I can start finding y. So 11 squared plus y squared equals 15 squared. 121 plus y squared equal 225. I'm going to subtract 121 from 225 and get myself 104. And I'm going to take the square root, and I'm going to go over here in my calculator, hit second square root of 104, and hit enter, and I get 10.19. So I get 10.2 for my value of y. Okay, so that's how I'm getting it, but you need to start recognizing the use of Pythagorean theorem and applying those theorems that we read about in situations like this, because remember, when you're first starting with this type of problem, they will not give you this dotted line. They'll just have this funky thing out here, and you have to kind of recognize that the consistency of radius is all the way around, so you can swing it around and make that right triangle. We know enough right now to be dangerous, and I want you to try this next one on your own, and I want you to use this as A. That's my help to you. You want to find X, but you can only use the information you have to find A, and it's a right triangle. Turn me off and give it a try. Okay, welcome back. Now, if you did this right, you should be pulling out the Pythagorean theorem using A as one of the sides. Okay, so I've got myself an A going on, and I flip-flop my theorem. I put this, I prepped this, and I'm not sure why I flipped it around, but I put C squared first, then B squared, and then A squared. I have no understanding of the reasoning why I did that for this one, but I did. But it still works the same. I got 225 equals 64 plus A squared. Now remember, this A is only half of the X that we're going to find. And I've got 225 equals 64. I subtract 64, I get 161. Again, I'm going to take the square root of 161, and I've got 12.68. So I'm looking at 12.68, but I've got two of them. There's a here and there's a here. So I have to multiply by 2. So 2 times 161 is 25.4, or I could just say times 2, my calculator, and I get that 25.4 as well. Now, that's the end of today's video, or this part 1 of the video. I hope things are going well, and have a great day.